No, that's the start button. The little red dot? Yeah. Hopefully we're recording right now. We'll see what happens. Alright, so very exciting day. We get to start the most difficult unit of the entire year. Woo! Isn't that exciting?
You said easiest, right?
Come on now, this is going to be, well, today's not hard. This isn't hard. And you're going to, we'll get through the notes. You're like, that doesn't seem that hard. But here's the deal. When people look back fondly at Calc 2, depending no matter where they have taken it, they would often say series is the most difficult stuff in Calc 2. And that was true for the students I had and other math teachers I know. But we're going to get you through it. So we're gonna some people really enjoy it, so maybe it won't be so bad. But we're going to go step by step, take our time. There's 2 chapters in your book that cover this. Usually this is the last unit of what we do in our plan, but with this book they actually put the unit on parametrics, polar, and vectors after this, which is kind of nice in terms of timing for us. So we'll definitely get through this before spring break, and then we might even start the next unit before spring break, if not right after spring break, and then that'll be it. And then we'll review for the AP exam. Okay? That's all we got. 2 tests left. That's it. So, Chapter 9, Sequences and Series. Sequences and Series. The very, very first question that we need to ask is, what is the difference between a sequence and a series? What is the difference between a sequence and a series? And don't feel bad if you don't know the answer, but let's see if we get any good tries out there. You've studied them, right? A lot. Yes, Mr. Guy, we did. Don't you remember pre-calculus you studied sequences and series, and in advanced algebra you studied sequences and series? Okay, now it's starting to come back. What is the difference between a sequence and a series? Did you just read that? I wanted to see if anybody do that without reading the book. Oh, that's all right. You're resourceful. You're right. A list of numbers. That's a sequence, a list of numbers. How does that differ from a series? What is a series? What do you think? They all have patterns. Oh, not necessarily have a pattern. I mean, they could be just any old listed number. They're both infinite. They could be adding or subtracting or multiplying, dividing within there to generate the terms. If I have my sequence, which is a list of numbers, and what am I going to do with my list of numbers? Usually, if we're talking about a series.
For a series, would you add all of them?
Excellent. Very good. So, a series is the sum of a list of numbers. Okay? That's the difference. For example, a sequence would be like 1, 3, 5, 7, 9. If it was an infinite sequence, it would go on forever and ever and ever. If it was finite, it would stop. Whereas a series, you would add the terms together. Okay, that's the difference. Please know that. If you can learn that, that's a good start. What's the difference between a sequence and a series? Now, we're going to spend some time today talking about sequences, probably about, 5-10 minutes. And then we're going to spend the next 3 weeks talking about series. So when you think about the amount of, content between the two, sequence is a really tiny part of what we do. And we'll talk about a little bit more there. Now, a couple other quick terms before we move on. about sequences. As I just mentioned, finite would mean there's a limited number of terms. And this is true for either one, a series or a sequence. It could be finite, limited number of terms, versus an infinite series or infinite sequence. The number of terms approaches infinity. Infinite number of terms. And this is, of course, going to start blowing your mind. We're going to add up, because it's a series, we're going to add them up. We're going to find the sum of an infinite number of terms. And sometimes we'll get an answer that's not infinity. We'll get like 5. Just like we found the area on a curve where the limit went to infinity. Sometimes we got an answer, and sometimes we didn't. When we got an answer for the integral, what did we call that? What did we say about that integral? It converged. So our main goal, if you could like take a big step back and say, what is going to happen for the next 3 weeks here? All we're doing is trying to determine if you're given a sequence, you're trying to determine if that converges or if it diverges. Or if you're given a series, you're trying to decide if that converges or diverges. That's it. That's pretty much the bulk of what we're going to be doing. Okay? So, as I said, let's start with sequence, the convergence of a sequence. So when we're trying to establish whether or not a sequence converges, really the question we're just asking is do the terms approach a value as the number of terms as the term, maybe we'll say the term number, that might be a better way of saying it, as the term number approaches infinity. For example, the one we've been dealing with, now this a sub n, this is just, we would a lot of times use that to represent the formula that's generating the terms. So let's say that's 2n, not sub n, 2n minus 1. That's a sub n. And that little formula generates, as you may be familiar with, you're going to be familiar with, you got to know right now, that generates the odd numbers. Because when you start with n equals 1, so you put 1 in for n, this is term number 1, and you get 1. And when you put in 2, term 2, you're going to get 3, 5, 7, 9, so on. Yeah, David.
Can you have a term number be like -1 or -5?
You could, technically. It would be really unusual. But it's not unusual to start with term number 0, to start with a 0 term. That's very common. And you could start, they might start you off with term number 4. It is possible to, because it is just a counter, so it is possible to say, I want you to start at term number 1, -1 or -2 or something like that. Okay? You just won't see it probably. Alright, so there we go. There's our sequence there. So the question is, are these numbers approaching a number, an actual value? Somebody already said infinity. What's the trouble with it? They're approaching infinity, right? But what's the trouble with infinity? Not a number. So this is approaching infinity. So therefore, this diverges. So the answer is no, they're not. They approach infinity instead. Diverges. this sequence diverges. And the way you could tell for sure, if you couldn't just tell by looking at it, would be, of course, to take the limit as n approaches infinity, because that's what we really want to know. As n approaches infinity, what are these values approaching? And if you put infinity in there, you get 2 times infinity minus 1, which is infinity. Lots and lots and lots of limits in this unit. Lots of them. A lot of fun with limits. Okay, if you drew a graph, you could tell too. If you thought about it here, graphing this out, 1, 2, 3, these are the term numbers. And we got 1, then 3, then 5. It's going to grow, exponentially. You're going to see that they're approaching infinity there. So that's another way of looking at it. So that's in contrast. Let's do one where it will converge. Just kind of giving it away here. So let's say instead we have this example. A sub n is 1 over n. So now we put 1 in first. We get 1. We put in 2. We get 1/2. Then 1/3. 1/4. Again, don't put a plus sign. This is a sequence, not a series. 1/5, and so on. Are those values approaching a number? Yes, they are. What is the value they are approaching? 0. Wonderful. So we would say this converges. Okay, this sequence converges. It converges to 0. And again, you could take the limit as n approaches infinity of 1 over n, and a number over infinity is equal to 0. You could also graph it out, and you would see the values would go like that. Now, does the answer have to be 0 if it converges? No, it doesn't. So, maybe you're going to have a series sequence, that converges to 2. The values as you go along are getting closer and closer to 2. That would converge. The limit as n approaches infinity of whatever this is would equal 2. And that's fine. They're going to throw some terms at you in the homework. It's nice to know these terms or seen them before. It's not really that essential. I mean, depending on in college, you're going to professors certainly going to throw them at you, especially when you're talking about proofs. They're going to talk about bounded. This is all bounded means, that it's never going to go past this 2. It's like an asymptote. Okay, that's what I mean by bounded. And then they're going to throw at you a monotonic. Monotonic just means it's moving in the same direction. So this is all either increasing, they call it non-decreasing. You think? Non-decreasing. Doesn't that mean increasing? Well, yeah, except non-decreasing means increasing or staying the same, right? It's flat. So that's why they get the idea. So that's what they mean. If you see monotonic, don't get all bent out of shape. That's all they mean by that. Okay? That's it for sequences. You will probably get maybe one question on your AP test about a sequence. And unfortunately, they throw people off all the time, because here we go. We're going to now start this adventure of spending hours and hours and hours and hours talking about series. And you're going to learn all these different ways of determining if a series converges. And you're going to be so focused on that, you're going to get your AP test and you're going to read the question and it's going to say, does the sequence converge? And you're going to not read it very carefully and you think the word said series. Can you see that happening? And now all they're asking is a pretty simple question here. Just take the limit as approaches infinity. That's all we want to do. Don't get into all the other stuff you did for the next 3 weeks. So don't forget, read the directions carefully. This is a sequence. That's all we need to do. This is it. That's all we're doing for sequences. But series is a whole nother game. So, convergence of a series. Since it's a series, the question is all about the sum. Does the sum approach a value as the term number approaches infinity? So now we're talking about the sum. Some of them are really easy and obvious. Let's go back to that same one we've been doing all along. 1 plus 3 plus 5, this odd generating odd numbers. You gotta keep adding those up. Will the sum approach a number? Is it, yeah, if you were to stop thinking about it, it should be pretty obvious, right? We're just going to keep adding larger and larger numbers on. It's just going to keep being bigger and bigger and bigger. So this would just end up being infinity. So the answer is no. That means this series diverges. What is the only possible way the series could converge? What has to be true about those numbers? Yeah.
Sequence will also converge.
Okay, and not just converge, but converge to what? 0, right? Because they could have converged to 2, and then you just start adding 2's on, and that's still not going to. But we want to make sure the numbers we start adding on at some point are approaching 0. So we're not really adding anything on that it's not changing the total amount. Okay, so conceptually, do you understand? Yeah. Yeah, they have to be getting smaller and smaller and smaller and smaller. Yeah, they have to be non-increasing or approaching monotonic and approaching, you know what I'm saying? They're approaching 0. So, the only way it is possible for a series to converge is if the terms approach 0. That's the only way it has a chance. So using the one that we had, 1 over n, for an example, 1 plus 1/2 plus 1/3 plus 1/4.
So approaching 0 just means it gets smaller.
Yes, I mean that's a simple way to think about it. But not only getting smaller, because like they could start at 5 and they could approach 2, and then just flatten out at 2. It's got to approach 0, so they're getting smaller and they're approaching 0. Now, it could be getting bigger. You could have negative terms. They could be getting bigger, but they're approaching 0. They could be going back and forth, oscillating, positive, negative, positive, negative, positive, negative. But the values have to be approaching 0. Because, why? I mean, why do they have to be approaching 0? Why? Perfect. Okay? So we have to get to a point where we're just adding 0 on. If we're only adding 0 on, then it's not changing, and now we can say what it is. So, are these values approaching 0? Yes, they are. Do we know this converges? Does it have a chance to converge? Could it possibly converge?
Yes.
It could possibly converge. Guess what? Do you think they know at this point it converges? No, because if we did, this would be the end of the series unit, right? That would be very exciting. 1 20-minute notes instead of 3 weeks. It's a big fat, I don't know what it equals, it's a maybe. when we did integrals, the only way they could possibly converge is if, again, it approached 0. But just because it did not mean you're going to get an answer. Sometimes you did, sometimes you didn't. And we used limits with the integral to try to figure that out. This is a different story. Here, so first of all, just write down, you can't tell by just looking. You must do a test. And by a test, I mean like a procedure, a way of evaluating if it converges or not. So you have to do a test to find out. And there isn't one test. The test you use the test used depends on the series. The test used depends on the type of series. What kind of series do you know so far? Geometric, nice. That's actually going to be the first one we talk about today. Geometric. What makes a geometric series a geometric series? Excellent. So you multiply to get the next term. You multiply every term by the same value to get to the next term. Okay? Give me another series that you learned. Arithmetic. What makes an arithmetic series an arithmetic series? You add. Perfect. And that could include adding a negative number, which some people think of subtraction, but you would add. Do you think those are the only two types of series?
No.
Wouldn't that be nice?
Powers.
We would really probably be able to finish soon. No. You could do a combination of adding, subtracting, multiplying, or dividing, right? Then it wouldn't be either one of them. You could spice it up. You could throw some trigonometry in there. You could put in sine and cosine in there, right? Or tangent or something like that. You could put some variables in the exponent. You could have like 2 to the n or something like that. You could have e to the x in there. You're going to see a lot of series that have factorial. Remember factorial? N factorial. 5 factorial. It doesn't mean 5 is really excited. What's 5 factorial? Exclamation mark, yeah.
5 plus 4 plus 3 plus 2.
Yeah. So, as you can tell, there are a whole bunch of different kinds of series. You're going to use a test depending on what type of series. Here's the good news. There are about 10 tests. I don't know, does that sound good? Like a manageable amount or not a manageable amount? 10. You're going to have about 10 tests. That's it. You got to know them all. You got to know their name, you got to know how to do them, you got to know when to use them, and you got to know what the results mean. Okay? And that's what we're going to spend a bulk of our time on. Testing to see if these things converge. Alright, let's go to our first type of series. So, different types of series. The very first one, geometric. And as we already stated, it's geometric because you multiply to get the next term. Multiply by that same value. It's called the ratio, the R value. Before we get too far along, let's just do a quick review here, because sometimes people don't quite remember. Let's just do a quick review of what series notation looks like. So, remember, we're adding up, it's a sum, it's the capital sigma. That's what you use to indicate that you want to add them up. You have a counter on sigma. You have to say where you're starting. A lot of times they use the letter N for your counter. K is another really common letter that's used for the counter. It could be any letter, really. So that's just your counter. You have to start somewhere. Geometric you almost always should be starting at 0. Other ones you might start at 1 or 2, it depends, but you got to start somewhere, and you got to end somewhere. And if we have an infinite series, then we're going to go to infinity. So there's your counter. And then you have a formula that's some kind of equation that's going to generate each of those terms. And n is the term number. So here is just what series notation looks like in general. Okay, and you're going to see a lot of interesting looking series. But for geometric, start you with a nice easy one that you're familiar with. So summation, we will start at 0. And I know in a lot of pre-calculus books they start you at 1, but I would really get in the habit of just always trying to start at 0 or thinking about it that way. And you'll see why here in a moment. We're going to go to infinity. And then what makes it a geometric series is that you have this r value, this ratio that you're multiplying. So you have a starting amount. And I don't know, I probably should have picked a different letter. It's not, it's a. This is just a constant. This is a number. This is your starting amount. This is your initial value or amount. I like to call this the 0 term. That helps me because, in other words, that's what you get when you put 0 in for n. It's the 0 term. And then you have r, which is your ratio. That's what you're multiplying by every time. And then, of course, that's to the n power. So the first time around, you put 0 in for n, and you get r to the 0, which is 1, and 1 times a is a, and that's why it's the 0 term. When you put in 1, you're going to get r to the first, r times a, so you just keep multiplying that by r every time. All right, so let's take a look at an example here quick. Let's say we have the summation equals 0. Let's say we start 4, r value is 1/3 to the n. So there's a good little easy one to begin with. We could find the terms. We would start with 0, put that in. We get the 4, which makes sense. That's our 0 term. We put in 1, and we get 4 times 1/3. We put in 2, and we get 4 times 1/9. 4 times 1/27, and so on. Does this have a chance to converge? Are those values approaching 0? Yes, they are. Okay, now, you might not even know what the answer to this is. There is a simple way to find out if this is converging or not. You learned it last year. Heather?
I have a question.
Yes.
I feel like, so, the term, not the initial value term, like, are we just looking at that one? Because technically, aren't they approaching 4? Like,
Oh, you're talking about what's happening? Yeah.
it's like the obviously the 1/3, the 1/9, the 1/27 are approaching 0, but like each term, like, this isn't the term, like.
So like this is 4/27s,
Okay.
this is 4/9s,
So
this is 4/3. Yeah, no, I'm glad you asked. So these values are getting smaller and smaller and smaller. You're adding stuff on, but what you're adding on is getting smaller, and as a matter of fact, the stuff you're adding on is approaching 0.
Yeah.
What's the only way that could happen? Okay, and so you're multiplying to get the next number, so what has to be true here in order for these values to be getting smaller?
Your ratio has to be less than 1.
Yeah, remember talking about that? It's got to be getting, if you're multiplying to get the next number, you got to multiply by a number less than 1 to get a smaller number. You're trying to find part of whatever you had before, okay? So this is technically the test, the first test. This is called the geometric series test. And it just simply says, look at that r value. If the absolute value of r, because you can have a negative r and you're still okay. You can have negative, that's fine. But the absolute value of r has to be less than 1. If that's true, then it will converge. Bennett.
For some reason I recall having the n be n minus 1.
Okay, I'm glad you said that. Yes, and so you probably had a pre-calculus book that started at 1 here. So if you start at 1, then you have to make an adjustment on the exponent up here of n minus 1. I would highly recommend to start at 0 and just remember this formula. Yeah?
Would it converge if r was 1?
Good question. What if it is 1? What does it mean for r to be 1? If I start with 4, what's the next number?
4.
And the next number?
4.
And I start, now the sequence converges, right? But does the series converge? Yeah, okay. So it has to be less than 1. If it was equal to or greater than 1, then it diverges. Okay. A follow-up question, which will most likely occur for geometric problems, is what is the sum if it converges? And I know you probably don't remember this because you should have really memorized this formula at one point. It would have helped on ACT for sure. But there's a formula to figure it out. So if this is your geometric problem, oops, yeah, that looks good. So A is that 0 term, R to the n, R is your ratio. Anybody remember the little formula? Maybe.
What's that SN thing?
It's the sum. Sn you can use for the sum, so sometimes they'll abbreviate it like this, Sn equals. It's just a beautiful little formula. It's amazing that it works out this way. A, that's starting, that 0 term, over 1 minus r. And you can see that listed like this. This is it. How cool is that? Think about this. Let's do the one we just did there. I think it was 1/3, wasn't it? So, will this converge? Yes. What will it converge to? What will the series converge to? What will the series equal when you're done adding up an infinite number of terms? I'm going to take an infinite number of numbers, I'm going to add them all up, and that answer is going to equal exactly 1 minus 4 over 1 minus 3, which is 4 over 2/3. And that's equal to 4 times 3 over 2. You get 6. 6, exactly. Not only is it amazing that you get an answer, that you can simply find the answer by that little formula right there. Isn't that cool?
I have a feeling that's going to be the only easy equation.
Hold on to that thought for a moment there. Yes?
So if you have to do this operation an infinite amount of times, how do you know how do you confirm whether that works if I were to be
Isn't that crazy? Yeah. And you know what? I can't remember the age of the guy that figured this out. I don't know. I'll have to look up back and see. I don't know if this is as true. Like, if this was Gauss figured out a formula similar to this, add up this n number of numbers, you know. He was like in kindergarten when he figured it out. Yeah, and the teacher said, stop bugging me. I mean, the kid knew everything. He had the answer. He said, go in the corner and add up the numbers 1 through 100. And like in 2 minutes, he comes back not only the solution, but he came back with the formula that we still use today of how to add up consecutive integers. Isn't that crazy? Okay, let's do a story problem example. So I know that many people at this point are asking themselves, when are we ever going to use this stuff? Well, here's a story problem. Not that this story problem really is, although it's pretty common in the world of calculus, this problem we'll talk about. But there are so many applications to this, it's going to really kind of blow your mind. You just don't know enough yet for me to be able to show you the applications, but when we get through the thing, you'll be like, wow. I didn't realize that thing I paid $100 for pretty much would only add, subtract, multiply, and divide if it wasn't for infinite series. Like, this is the solution to how to get that calculator to do what it does. That's what's amazing about it. Okay? But this little problem, I'll call the bouncing ball problem.
Oh, is it not the bouncy ball?
So, I don't know why it is, this is a common problem for this geometric. In the world of calculus, for some reason, you got your ladder sliding down a wall, you got your conical tanks dripping with water. What else you got? People walking towards lampposts. Here's another very common issue, balls bouncing on the ground. Okay, so you drop a ball like a Super Bowl, I guess, from 50 feet. And the ball bounces 2/3 of the previous height. How far does the ball travel? So here's what's going on. We have this ball. We drop it from 50 feet, and it starts bouncing. It always goes up 2/3 of whatever that previous height was. And it's a geometric situation because every single time is 2/3. So we're going to write a geometric series to be able to calculate this. So you get really excited because you think, I got this. Starting height was 50. That looks good. Your R value, well, it's 2/3. All that's looking great. The height, you think, okay, well, that would just equal the summation of A, which is 50, over 1 minus 2/3. So that's equal to 50 over 1/3, which is 150. And you're really excited because you look and you see choice C on your test and you circle it or bubble it in, and it's wrong. What did you do wrong?
That only accounts for the trip up.
Yeah. You just found that. So, you think, all right, it went up and down. What are we going to do to this value? Double it. So you times it by 2, and you get 300. And then you're really excited because you see choice A is 300, and you get it wrong.
What did it count for?
It was just the trip up or the trip down one way. So we times it by 2 to go up and down, up and down, up and down. Well, yeah. Can you see that tricking people? That one was only 1. Didn't go up for that one. So what are we going to do to this answer? Don't want to add 50. What are we going to do? Subtract 50. We got 50 too much on there. 250 choice B, and that's the correct answer. Okay? Very common question. I don't know if they throw it on the AP test or not, but that's a similar idea to that. Here are other ways they're going to try to trick you on the AP test. I know it from my experience with looking at geometric problems. So let's start with this one. This isn't that tricky, I don't think. Hopefully this won't fool you. What's the answer to that? Maybe it is tricky.
Why is it such a hard answer?
Does it converge or diverge?
Diverge.
So what's the answer?
Infinite.
Infinity. That's what diverge means. You keep adding up, you're going to get infinity. This is infinity. Or they might just say diverges. Why?
R is
You got it. It's all that R value right there. That's so important. This stuff's really hard. It's even harder if you're sleeping. poke him so he knows that he's missing some important stuff. Okay, talk about this tricky problem. Sometimes it looks like they give you a problem you're not sure if it's geometric or not, and you have to do a little bit of work to make it geometric. Because geometric is r to the n, and this is r to the negative 2n. So now what do you want to do?
You just put the 5 to the negative second power, right?
So I'm going to rewrite it, right? Because I'm,
1 over 25.
yeah, so think about it this way. That's equivalent. When you multiply, you must have did a power to a power. So you're going to rewrite it like this. So here is your r value, which probably better to think of it like this. And now you see that you can find the sum of that. What is my a value here? 1. So it'll be 1 over 1 minus 25, whatever that is. 25, 24s, I guess, right? Okay? And then here's another one. There are going to be other ones that are tricky like that. You have to rewrite the problem. Here, let's do this one. This fools people every time. You can just sit here in a hurry, a time limit, you're rushing along, everything. Because it looks really easy and straightforward, right? I mean, a is 2 minus 1/2, so you get 1/2. So 2 over 1/2, and that's 4. But that's wrong.
Because n equals 1.
Yeah, you see that? Can you see people messing that up? We don't want to start at the 0 term, we want to start at term when n equals 1. But we can still use this formula. You don't have to like create your own formula now. You can still use this formula. We just got too much. What do we got to do to that? So I just want to take off which term? The 0 term. I need to find the 0 term. The 0 term I know is 2. When I put 0 in here, I'm going to get 2. So I'm going to take off 2, and that's the answer. And again, they could start at any number. They could start at 3. That just means you find it like you would the formula, then subtract off the 0 term, the term when n equals 1, and the term when n equals 2. Take all of them off. Okay? Don't get fooled by that. Alright. One more test we're going to do today. This is a quick and easy one. It's called the telescoping series test. Telescoping series test. A very strange name. Yeah?
It's all still within the geometric series.
This is not a geometric series. This is another new series you've never heard of before. Oh, by the way, if you're trying to keep track of where we are, the sections all kind of blur together. So, I wouldn't try to worry about that. Just stop, listen, this is easy. Telescoping series. Well, the first part is you got to understand what they're talking about here. And I realized yesterday, you guys never played with a toy telescope when you were little, did you? You got iPads now and Nintendo and stuff like that. When I was a kid, we had plastic telescopes we ran around with. So in Jack Sparrow and the Pirates of the Caribbean, maybe that'll help you. It's a telescope. Not a telescope nowadays. You got this big, huge telescope that sits there on the deck, and you look through it. A telescope where it's it's a tube about this long, and you pull it apart, and it stretches out, so you can look through it. And when you're done, you push it back together, and you can put it in your pocket. Okay? This was a toy when we were a kid. This is what we did for fun. Okay? I had a lot of other played with rocks and sticks. I don't know, but
Rocks.
So, keep that in mind when I show you what a telescoping series looks like. It'll help you understand. So here I'm going to write it out, and you'll see they're kind of cool. on adding that up? Isn't that nice? So that you have this last term out here, which we don't, this is going to go to infinity or infinite term, right? Well, we realize that things are going to cancel. And that last term might not cancel, depends on when that last term is, and in theory it's infinity, so it's really weird to think about it. But all these terms in the middle cancel out. So that's why they say it's like a telescope. You take this series and you push it back together like you would your toy telescope, and you get to 3 plus the last term. That's why it's called a telescoping series. Yeah?
So we're just assuming that it lands on the nth term? That is the 3?
But we're not assuming anything. The last term is the nth term as n approaches infinity.
Are you assuming we have a negative 1/5?
No, I'm glad you asked. Okay, so how do you find the sum? This is the sum right here. Well, we need to know what this last term is, right? So we would take the sum is just going to equal the first term, or the first value, whatever it is, even if it's part of a term, plus the limit as n approaches infinity of whatever we're trying to find. Say the last term, a sub n. What are these approaching? What are all these values approaching here? 0. So this is why we know it's 3 plus 0, which you just did in your head. Bailey.
What if the last term cancels out with another term? Like, if we use what we have now, the negative 5 or the negative 1/5 and the positive 1/5 and the negative 5th would cancel.
Are you wondering if the last term will cancel with the term before?
Yeah, what if they canceled with the previous term, then we still add it on?
So let's talk a little philosophy. Will you ever have a last term?
Well, I mean, if you're just looking at a second.
Well, we're not,
Okay.
right? Because we're going to infinity. This is an infinite series. We're finding the sum. Interesting, isn't it? You're going to really enjoy a math major. Yeah.
Are we doing finite series?
Oh, what?
Are we doing finite series at all? Like,
Well, if you did, you would just find all the terms and add them together. And
I mean, like in general.
that's like, not really. That's like
It's not really connected.
child's play, right? I mean, you know what I'm saying? Is like find the first 5 terms and add them together. That was back in glory days. But now we're thinking infinite. The limit. The limit of all this stuff as it approaches infinity, those terms are approaching 0. That's why we know all this, regardless of where it ends, it's going to 0. And that's where it's going to work out. Is he running the same thing?
That reminds me of super.
Okay. Other questions on the telescope? That's it for telescoping series test, by the way. 2 of 10 tests. Yeah, David.
What's the equation for k plus?
Here's a great example. I think this is on the homework. Here's it over here. 1 over k plus 1 minus 1 over k plus 2. So you plug in 1 and you get 1/6. And people they're like, I don't get it. I don't see it. Well, don't plug it all in. Look at each. So this is the first term. This is the second term. This is the third term. And then when you look at that, you can realize, they're going to cancel out. I can see where it's going. Now, these values were approaching a number, like if they're approaching 1 for some reason instead of 0, then you know that the last term is 1 plus this term here. But they're approaching 0, so all that stuff will cancel out. In the end, you're going to get 0, and so you just get 1/2 here. Even though this stuff, 1/2 minus 1/3, this was all the first term with the 0 term. Okay? So don't put too much thought. You might get 1 problem on the AP test that's telescope series, maybe 1, if you're lucky, and it'll be easy because you'll realize, I just put the numbers in and realize, they just cancel out, so I know what I'm going to get.
It's like that's when we know, is it?
Yeah, I mean, you just know it. It just doesn't come up. And then, so go back to Marcus' question. He said, I bet you the other formulas to finding the sum are more difficult. And so, these are the only 2 types of series you will ever be asked to find the actual sum. Because he's right. Everything else, it's so hard to find the sum, they say don't even try. Just tell me if it's going to converge or not. Okay? So, geometric, telescoping, besides knowing if it converges or diverges, you'll have to find the sum. Everything else, it pretty much is just to figure out if it converges or not. What's that?
Are you gonna make us find something you don't have?
No.
Thank you.
All right, here is your assignment.
This is you.
Well, I did like throw it back.
I think I need to find a new life course here. I'm gonna go and study music. What is A sharp plus G flat?
I have some knowledge in philosophy, so I can give you a better question than your original question about how do you know to ask her.
If there's a better question, I don't want to know. There's another question.
You can do anything.
Okay, so there were 3 sections, but 9.1 it was like this overview thing, and there were, in my opinion, there weren't any problems worthwhile to give you in that section. So just 9.2 and 9.3, that's where the problems are coming from. You got so much time. There were people last hour for sure that got this whole thing done, or almost done to the last problem or 2 when they finished. Now, help me out. You know, Luke Schoberly came in this morning. You guys know Luke. I love Luke because he's always my little guinea pig. He goes home and does the whole assignment, comes back and tells me the problems that were crazy that I shouldn't have assigned. Yeah, oh yeah. That is great. I'm going to miss Luke. So, well, first, hopefully we'll get it all figured out before he leaves. So we are just thing, Luke, when I cross these 2 off here, 79 and 81. You have no idea what you're getting yourself out of, but it's a good thing. Please do me a favor and send a message to your friends, doesn't have to be this second, that if they are in 5th hour, they don't know this, so make sure they know they can take off 79 and 81, okay?
And then when they ask for help, make them process that.
So don't be mean, let them know because